Hello everyone, welcome to my new lecture. So in this lecture, we will discuss about the nanoparticle production using the supercritical fluids. So first of all, supercritical fluids are defined as those substances whose temperature and pressure have been raised above the point where the densities of the liquids and gas states are the same. So whenever the substances they are exist in a supercritical state, they can be used as a solvents or anti-solvents and hence used in the production of particulates in a similar manner to other solvent system. This lecture is related with nanoparticle productions by using the supercritical fluids. Actually, these are those fluids whose temperature and pressures they are always elevate and rise above the point when the density of the liquids and gas states they are the same. The use of supercritical fluids has increased significantly over the last few years, with many drugs either being encapsulated within or being formed into the nanoparticles using this technique. However, there are a number of advantages to using the supercritical fluids over the conventional solvent system. Production is usually a one-step process with little polydispersity and the particle size, and perhaps most importantly much less organic solvent is used, with carbon dioxides being the most frequently used supercritical fluids. This is obviously of significance environmentally, especially if the production is on the commercial scales. The number of techniques they are totally based on the supercritical fluid technology. So three of the particular pharmaceutical interest, namely the supercritical anti-solvent that is also called SAS, supercritical anti-solvent, and the rapid expansion of the supercritical solutions that is called the rapid expansion of supercritical solutions methods, and the gas anti-solvent that is also gas anti-solvent technique they are also applicables. The SAS or the supercritical anti-solvent methods involve the introduction of the supercritical fluid into a solution of the solute in an organic solvent. At high pressure, the fluids act as an anti-solvent, becoming soluble enough in the organic solvent to precipitate out the solute. At the final operating pressure, the supercritical fluids flow through the precipitations vessel, stripping away any residual organic solvent. Finally, the vessel is depressurized and a solid product is collected. The gas technique is a modified version of this method, with the organic solution being rapidly introduced into the supercritical fluid through a fine nozzle. So the solution is quickly extracted into the fluid, resulting in instantaneous precipitation of solute as fine particles. In RESS method, the solute of interest is solubilized in a supercritical fluids, which is then rapidly expanded through a nozzles. As the fluid expands, so it loses its solvent's capabilities and the solute precipitate out. While this technique has the advantage of not using any organic solvent, so it is restricted by the generally poor solubility of the most polymers and supercritical fluids. Indeed, polymers generally have to below 10,000 molecular weight in order to eligible for this method of particle productions. So you can see here on my screen where D is the diffusion coefficient and K is the Boltzmann constant, while T is the absolute temperature, and this lambda n is used for the viscosity, which is the internal resistance to the flow of liquids. and DH is the hydrodynamic diameter. The hydrodynamics diameter or Stokes diameter measures how a particle moves within a fluid. To obtain the mass or volume diameter, the full Mie theory should be used, which required the knowledge of the refractive index of the particulate material and sizing medium. The upper limit of the size for BCS is determined by the density of the particle and most importantly its onset of sedimentations, that rather than limitation on the technique itself. PCS is a rapid, non-destructive technique which enables the measurement of many types of spherically shaped entities including the discrete living cells without causing alterations or damage. However, the use of PCS is not possible when the size distribution of the sample is broad, the sample material is non-spherical, and multimodal distributions are present. PCS is also susceptible to the error from the presence of larger particles such as dust, microbial contamination, crystallization of ingredients, or secondary particles agglomerates. Larger particles scatters more light than smaller particles, as shown by the Rayleigh ratios, and thus it will swim the scattered light from the smaller particles. Samples for PCS measurements must be cleaned and filtered to ensure the removal of contaminating dust particles. Another disadvantage of this method is that the particle size is influenced by the surrounding medium, such as absorbed surfactants or hydration layers. PCS has been applied in nanoparticulate characterization to investigate the effect of altering preparation parameter on the particle size of various nanoparticulate carriers such as polyalkyl cyanoacrylates. The effect of the incorporation of the drugs on nanoparticles on nanoparticle size has also been investigated. PCS has been used to examine the degradation of PSA nanoparticle, and this technique has been useful in determining the influence on the size of using different surfactants and preparation process, and also the thickness of surfactants coatings layer on the surface of nanoparticles. So you know better, there is another technique which is called electron microscopy technique, that is called SEM, which can be represented by a capital letter SEM and TEM. Transmission electron microscopy have been used to measure the particle size of nanoparticles. So the particle size or the nanoparticles, it can be determined with the help of electron microscopy technique or transmission electron microscopy. TEM has the additional advantage in this interior particle morphology can be determined by the freeze fracturings. Transmission electron microscopy has been used to size the polyacyclic acid and cellulose nanoparticles, so it was shown that the size obtained were comparable to PCS. TEM has been used to optimize the preparation condition of the polymethyl methacrylates nanoparticle to obtain the small particle size. Scanning electron microscopy required the particle to be coated with the gold to make them conductive, and this coating varies in thickness from 30 to 60 nanometer, which has to be subtracted in order to determine the size of the uncoated particles. While on comparison to the other sizing technique, the particle size of polyacrylic acid nanoparticle by the SEM scanning electron microscopy were in good agreement. Although electron microscopy allows the measurement of the individual particle, this may be unrepresentative of the whole sample, and the low vacuum used like gold coatings and any other surfactant presents, it may alter the particle size. So Thank you so much for watching my lecture. So if you have any question, so I'm always available. You can directly email me, and inshallah my next presentation topic is surface charge.